Everyone. Welcome everyone to ICAX Talks, Youth Talks. We are so proud that every day every week we have a wonderful young talents on this stage. Yeah, Alice Zhang was from Peking University, so the founder of this I Can X Talks. So it's very exciting, to listen to all these young talks, youth talks, and Tuesday. Today we have a group, yeah, was the leading scientists in the micro nanorobots and organ on the chip. So we have three speakers from a different part of Asia. We also have two beautiful panelists was my neighborhood. Yeah, so we will introduce them one by one. So our first speaker today is Professor Feng Lin. Actually, Feng Lin was, this picture may looks like, is a teenager, yeah, very young. But I tell you that because he's doing a lot of work for AI, so he, use AI modified his picture. Yeah, actually, but of course, Feng Lin is the most handsome, professor in Beihang University, and Feng Lin has. Got a degree was from Japan, also not that long time ago, and then he got experience in the industry, and then back to China as a professor in Beihang. And he win a lot of awards. Actually, he is now listed as a National Young Scientist Changjiang Scholar, Young Changjiang Scholar. That's a big title, and he also is a Beijing Rising Star in Science and Technology. And he was hosting many conference. And he was, as a editor of the journals, Robots Research, Small and Lab on Chip, and all this. So Lin was really active and did a lot of work for micro nano robots, but also Lin has, very good experience to, get the results to be commercialized. So yeah, Feng Lin, without further ado, the stage is yours. Please share your story with us, please.
Okay, thank you. Okay, let me share my screen. Oh, can you see my screen?
I mean, yes, beautiful.
Okay, great. Um, First of all, I would like to express my sincere gratitude to Professor Zhang Haixia for inviting me to organize this small seminar for the young scholars. And I'm glad to give a brief introduction to my research work. So generally, today's topic is optoelectronic-tweezer, micromanipulations, and magnetically controlled micronanorobot. So first of all, let me ask you guys a question. Do you want to be an X-Men? Yeah, actually, I took a lot of the footage from the X-Men on this page. This is the first main character, Magneto. So I think if you love the Marvel movies, you can find out these screens, yeah, footage from the movie. And this is another footage screen. And finally, I would like to show the Magneto, like he controlled a lot of the magnetic materials. And yeah, so I think everybody's watched this movie and they want to have such kind of a superpower. And then the second question is, how do you become the Magneto or the scalar witch? And you can control something and levitate something in the air. So that's going to be interesting, right? So I think the answer is you need to learn how to control the electromagnetic field. This may be the easy way to achieve the superpower, yeah, as a superhero. So then I would like to let's get back to the topic of the today's talk. So first, I would like to introduce the background of the micronanorobot. So micronanorobot generally is a combination with the micronano size object plus the robotics technology and the non-contact control. So generally, we focusing on control the things in the small scale. Yeah. So mostly the size is from the 10 nanometer to 10 centimeter. And the thing, by using the non-contact control technology, it shows less damage to the environment and non-invasive control to the like cells or the human body. So, and then the micro nano robot, we are focusing on the more accurate control in the micro nano positioning accuracy. So first, I would like to introduce a little bit the history of the micronanorobot. So generally, in our research field, people would like to see the first person who said who gave a talk in the Nobel Prize conference. He is a quite famous physicist. His name is Feynman. I think most of the people know him very well. And he said there is a plenty of room in the at the bottom. That means except the aerospace, like the we set the satellite or the rocket in the space. In the contrast, actually, there is a lot of room in the micro nano scales. There is a famous movie, a Hollywood movie. His name is Fantastic Voyage. It said that they changed it's a sci-fi movie. It shows the doctors in the small scales and goes into the human body and try to do the surgeries in our human body. And after that, by the development of the MEMS technology, from the 1970 to the 1990s, the development with MEMS technology, we can manufacture the things in the very small scales. And then after the 2000, I think there is a quite popular with a lot of people who get into this research field, into the micro nano field research. At the beginning, people try to using the chemical way to drive the micro nano robot, like in these pictures, using some chemical reactions. And from the 2009, Professor Brad Nielsen in the ETH, he published a paper, and they said they can make the micro nano robot into 20 micrometers. After that, people try to make the micro nano robot even smaller and goes into the nano scales. And for the control of the micro nano robot, because it's hard to carry some batteries or the powers on the micro nano robot, so the control by using the magnetic field or the light field or the acoustic or the electric field is widely used to control the micro nano robot. And after the 2010, people try to put the micro nano robot in the human eye or in our human bodies, like organs and digestive systems. And these pictures is published by our groups. We published many different kinds of micro nano robots, and we also tried some experiment by using the mouse, by using the real animals, and to see if it can really kill the cancers. And for the micro nano robot, it have a wide applications. For example, this is another famous animation. It can change the micro nano robot shapes into the different shapes. And for the drug deliveries, we can using the soft material to deliver the drug, or killing the cancer, or clean the blood vessel blockage and cell manipulation. This is using the micro nano robot carry a sperm and to do the fertilization, or using the kinesin. And actually, this is not a human manufactured micro nano robot. As I told you guys, the micro nano robot, the definition is quite wide. Everything we can control to achieve some tasks, we call them micro nano robots. Then I would like to focusing on the main research work in my lab. In our lab, we are focusing on the micro nano robot and the micro manipulations. we made some big robot in the like a capsule robot. We like swallow them into the digestive system, and we can check if there are some problems in your digestive system. And we made some cell robots and a small size cell robot. For the manipulation part, we did the optoelectronic-tweezer manipulations and also using the magnetic field to do the manipulations. Today, I would like to focusing on the optoelectronic-tweezer manipulation and the cell robot. And this is shows the main research topic. What I'm gonna to introduce first is a magnetic control, and second is a light control. Actually, I started a company and I try to make these technologies into some real product. Okay, so first I would like to introduce the Micronanorobot for the drug delivery technologies. And actually, in China, every 1 minute there are 9 people diagnosed cancer, and 6 people died because of this cancer. And for the anti-tumor target drug, there is 200 billion RMB per year. So in the 2021, Science published 125 cutting-edge scientific questions is asked. So will injectable disease-resistant nanorobots become a reality? So we are trying to answer these questions, and then we did a lot of research work on that. For the conventional cancer treatment, there is a problems with targeted drug delivery. Is the low targeted rate. Only 0.7% of the molecular targeted drug reach to the tumor location, and most of the drug is wasted by our body because you can see from this page. Most of the drugs, if we take after we take into our body, most of the drug will spread to all the human bodies everywhere. It goes to the everywhere, and we want to control the micronanorobot, which carried a drug to go to the direct position of the lung tumor or any kind of the tumors in our precise position. So this kind of technology shows a great advantage, like mobility is controllable, or the targeting is processed, and releasing the drugs, it can achieve the intelligent releasing of the drugs. And for the ultimate goal, we want to do is to improve 100 times from the 0.7% to at least 70%. And here show some big size. I would like to introduce our research work from big size to the small size. Okay, so first is a little bit big. It cannot see. It's like a micro nano robot. It's somehow like centimeters or millimeters. So this kind of the slime robot, it can do the stretching or the rolling as a combination and the spreading. Actually, we mixed some magnetic nanoparticles with some soft materials, and then it can change
instability of the controller. This is problematic for the computer vision tracking and anything. So then we have our idea at the time to make this fiction overcome by generating adaptively these high frequency vibrations, longitudinal or this vibration can allow to make this control of trajectory control smoothly and very long time. I mean, this is incomparable between the without vibrators. You guess, as you see, if you're passing to these regions, is getting stuck. Cycle of motions. but with the vibrator on, you can go almost until this controller gets switched off. So this, we use it to scan over on the surface. It means unknown surface in terms of the section, and we can generate a section map based on the real-time correct speed of the microchip. So as we have this real-time created section map, we can have optimal task planning to generate, to improve the position control accuracies and motion control longevity. So that with this proportion dynamics and also with this controllabilities, we have, as we said, is International Mobile Micro-Robotics Challenges. We have been participating 2010 as a French SNR's team, and we got 5 times of champion titles out of 7 participations. So first 2 challenges was on the proportion dynamics. Then 2013 was for the micro assembly challenges to assemble these tiny micro triangle structures end of the microchannels. Then also these mobility challenges for the obstacle avoidance. And more recently, 2017 in Singapore, it was the mobility and precision challenges. They were measuring the size of the robot, smaller one is better, and positioning accuracies, so the error of the trajectory, and also the programming time. They give us a trajectory plan, and we have to program within 2 minutes, and they measure how long we took to program our code. So it was quite, and this was quite, if I remember, was the almost the I think 2008 last event for micro challenges, and then we got this COVID-19. It stopped. Okay, then is what's the application of this micro streamer micro robot, and so I immediately fly to the Nagoya at the time from France. So the Professor Lin was there at the time, and I met him, and in this laboratory of Professor Arai lab in Shanghai University, they were working on this bovine oocyte egg cells and the manipulating and the physical property characterization. And of course, I proposed that why don't we use this microstreamer to make microstreamers for this concern? And so we had the first proof of concept to make this thanks to the collaboration with Nagoya universities. We can have these microstreamers to be able to characterize the mechanical properties of the biological cells. And with this collaboration with the University of Tokyo, Japan, so the manipulating with even tinier cells, smaller cells, compared to the 100 micrometer oocyte, but it's more like 10 micrometer neuron cells. And the neurobiologist wanted to make this somehow Lego-like reconfigurable manipulation of the neural cells to study their growth. And so the in Takeuchi's lab in University of Tokyo was building a mobile platform, mobile microplate, which is cells inside on this platform. Then they were using pipettes to manipulate, but then we used our microswimmers to manipulate this cell-laden mobile microplate. So we can imagine this assembly was done in microfluidic conditions and with microswimmers. And then this once the assembly was done, we can make this cell-to-cell bonding by cell proliferation to two different plates. As you see, the cell is the two plates are well bonded. And once we want to disassemble, we can disconnect this cell-to-cell bonding agent with trypsinations, and we can have this also physically disconnected by micro. So this allowed to make these tinier cell manipulations. But in the second part of my talk is also to talk about not the microscale swimmer, but nanoscale swimmers. So Professor Feng Lin showed in the introduction that the first example from helical microswimmers from ETH Zurich, Red Nursing Group. So in 2006 and between and 8, I have stayed in Red Nursing Group in ETH Zurich. At the time, my work was to design and develop these 3D helical structures based on the semiconductor films using the minimum microfabrication process and the strain engineering. The objective at the time was to not initially to develop this microswimmer, because this was fresh technologies. The first one objective was to make this metallic electrode, both sides of this helical structure. So this is a gold metal pad to allow to make electrical probing to test electrical and electromechanical property characterization. My work was to be able to pull and make this tensor elongation study while measuring the piezoelectric property, piezoresistivity property, and to make apply them as force sensors. But then, of course, in the Red Nursing group, I've seen that they try to put it in liquid environment, and they were swimming. So it was 2009, the first swimmer in the artificial flagella. So artificial bacteria flagella, it's was first made, but when you put it in liquid environment, you see that they get easily stuck to the surface channels in microfluidics. And as you see that they are semiconductor very fragile, they can easily break. And mechanically weak, and also they have very low dynamics, which is not able to overcome the external flow. So more recently, we have new technology, 3D printing in nanoscale, so based on 2-photon 3D nanolithography. Based on these technologies, we can create many different shapes of helical structures, which is more biocompatible rather than gallium arsenide semiconductor, which is toxic. And then we can put in microfluidic conditions. So when we design microfluidics, on the side wall of the microfluidic chip is shown here. So we integrate helical microswimmer from open chamber, and once the helical swimmer goes through the microchannel by swimming, and it's entered to the first chamber for the calibration, the proportion property is calibrated. And then second chamber is to picking up functionalization of the tip to make picking up functionalized bead by these helical streamers. And then the last chamber is for the testing chamber. And finally, we store them in storage for long-term storage. We show here the helical streamer swim into the trap, and trap is open now. Helical streamer inside, trap go down, and droplet encapsulated. We dry them quickly without damaging the streamers. And once it's dry, we can keep it for more than a year. Once we want open again, and the liquid goes in, helical streamers get back out of this trap. So this is important because we can calibrate helical streamers and we can store them, dry them, store them, and we can use it for the like a plug and play manner. So we can use it as micromanipulations or cell manipulation, or these force sensings. These helical streamers can pick tiny microbeads, enter to any micro capillaries or channels. Once it enter to the testing chamber, and we can make a measurement. And we can also use a streamer in a kind of atomic force microscope for the surface topography sensing. So we can make them streamer to scan over the surface. We can make obstacles, we can make surface topography sensing. So these streamers can be useful to make a surface analysis in a confined microchannel environment where we cannot really use this kind of external sensors. And we have also fundamental studied that to make these helical streamers to be able to robust in underflow. Underflow, streamer could carry away, we can lose it. But the strategy is to use a streamer adaptively to swim and to sediment the surface motion, depending on the flow rate. So this streamer has a flow sensing. Once flow is important, high enough, the streamer goes down to the surface. This is now doing surface motions. When the flow is decreased, the streamer goes back to swim 3D motions. Now is the stream trigger to the, and it continue make this 3D swim. Then another study we have done is to make these helical streamers in a tiny microchannels only by 2D of imaging, because most of medical or microscopies is 2D imaging is available and less computational cost. So the strategy is to use helical streamers to make this helical trajectory propulsion and to self-stabilize by the vertical flow generated around by rotation, and to goes to the center of the channels, and simply by detection of the yaw control, and we can make this stable motion even in bifurcated conditions.
Hi, Dr. Huang. Yeah, so
Yes.
we have 5 minutes. Yeah.
Okay. Yeah. Okay. I'm sorry. I have my slide is a bit stuck. Okay. Mm. Mm. So
Yeah, maybe, videos. I think there are many videos.
yeah,
They got some
my,
trouble.
my videos. Yeah. Okay. So
The computer stopped.
yeah, computer stuck. Can you see? Yeah.
Yeah, come in.
Okay.
Thank you.
So yeah. So okay. I have to be quick. Okay. So we are using this helical streamer in the microfluidic chips for the 3D non-contact manipulation. It's the first example we have demonstrated in the world to make 3D non-contact manipulation by vertical trapping, and it showed uh, by, as you see that this is this is 2D, and by vertical trapping is moving and through the trajectory, and we elaborated design to make their trapping in 3D environment. And we can have a new user interface, more interactive, for the users can make this control is more user friendly, and also the environmental detections and so on. So we have summarized all these micro and nano streamers. Very proportion dynamics is very important, and the controllabilities, and all they are in microfluidics integrated. So we can keep it for longer time. We can send it by post from Japan to France, the lab, that we can make a plug and play, which is important for the many applications. So now for recently, as we said, it's more for the we are shifting to more intelligent smart streamers or soft streamers, and now as you see here is more like a surface cleaner applications, so microfluidic cleaners by resonating motions streamers, and this very dirty environment. As you see, the microstreamer is working in very dirty environment, as you see, and it can also even clean the surface. And as you see, this is example of microstreamer as a micro cleaner. And this tiny agent, 3D microfractal pipette, this can allow to make absorb the biological samples and deliver them. And this can be mobile, and this can transport biological samples in air and liquid environment. So, and another last example, we are showing the soft streamers. This is compared to the rigid shape streamer, but these soft streamers, we can make these self deformations, and as we say, you can swim in microfluidics, and you can make deformation to allow to make these grasping manipulations, and also the liquid sample handling between two droplets. So you can wet surface, and you can deliver to another liquid droplet, and then we can mix them, and this we can iterate these operations. This is showing that this streamer can even then prepare the samples, biological sample. We can take it to the biosensor kit, and we can measure this. We can make these biosensing applications. Okay, so this is also the manipulation, so, but I don't have time last. So okay, the last things we are now is last talk is about artificial organ, if I remember. So I'm talking a little bit to finish with the. So we are also working in artificial organ because we before we want to test in vivo environment. So here we are developing an artificial lung device, and this is showing this. So yeah, so this we are building different types of artificial organ today. So artificial lung and for the pulmon oxygenators, microfluidic oxygenator applications, and also the cancer assessment, artificial organs, and many different types of organs. So today I don't have time to cover all, but in near futures, we want to have some merging between the microstreamer and the artificial organs. But this is my team. We have contributed from France to from Japan, and thank you very much for your attention with the sakura cherry blossom photo.
God, I remember this tree. I have a take a picture many years ago with Professor Fujita.
This
The
is
same
exactly same
the same
place.
tree.
Yeah,
Yeah, the
and
same
same
place, the
tree.
same tree. Yes.
And this today is really the peak of this cherry blossom in Japan.
Yes, yes. I
The-
think I came
yes,
that time, the same thing, very beautiful.
yes.
I remember this tree. So great. Congratulations. You have done
Yeah,
so many things. I'm so
yeah.
proud of that to meet you this time because, 2009, that job, with the swimmer first come out,
Yes,
the structures. We follow that paper. So we think that's
yes.
amazing. Yeah. Yeah.
And
Also,
Zhang was at the time and in the brand nursing group in ETH. I was there. Yeah, we met him.
yes,
Yeah.
great. Yeah. So, yes, yeah, we save some time for the discussion to the panel.
Okay.
Yeah. So,
Okay.
yeah, let me
Yeah.
introduce the third speaker as Professor
Okay.
Tao Yue. So Yue was got PhD was from Nagoya University. I think it's the Toshi Fukuda, right? Yeah. So
Yeah.
Professor Toshi Fukuda was leading a big group. I think more than 100 PhD, right? Yeah, including
Yes.
Feng Lin and you. So Yue was win a lot of honors during the PhD. I see you win the best papers in the IEEE conference, and also the Young Scientist Award. And you also get the Shanghai Young Oriental, scholars in 2017. I think that's the reason you're back to Shanghai. So yeah, so now is a rising star there. Also get the third prize of award of the technology invention of Shanghai in 2022. So meanings you really got into your job so quickly. In few years you got some honors. So yes, stage is yours. Share your story, please.
Okay. Thank you. I will first share my screen. Do you see the screen, Professor Tang?
Yes, full
Okay,
screen,
that's
please.
good. Okay, so it's my pleasure to be here. First, I have to I would like to express my heartfelt gratitude to Professor Zhang. And as I mentioned, I went to a lab 10 years ago. It's it's a very memorable time back to Beijing. And today it's my honor to be here to share with you guys some of my research. And as you see that I come from Shanghai University, so we have a school, it's mechatronics and automation. So actually, it's a combination of mechanics and control and automation. So we have many different like research topics. So we have a center. It's called Micro Nano Manipulation Center. So now I'm working in this center as the director. Today I have many things to talk, but I think it's a good chance to introduce our group and as well as our one of our key research topic, which is vascularized organ-on-a-chip. I think now it's very it's a hot research field in micronano. So I think today it's a good time. So first, as I mentioned, I think it's a good time for me to introduce our research center as the first content, and then I will move to the key topic about organ-on-a-chip. So our organ-chip is it's a special one, which means we have put the micro vessels, which is perfusable. It means the flow can go through the whole chip. This is I think it's a unique type of organ-on-chip. So today I will talk this part as the key contents, and then I give some conclusions. So first, about the research center I mentioned in Shanghai University. Still, we follow the same thing like the Professor Feng, as mentioned. Today, I also thank Professor Feng give me the chance to present here. He mentioned that the great scientist, Richard Feynman, he mentioned that there's plenty of room at the bottom, which means that we if we want to solve something, or if we want to make like watch the real phenomenon of something, that means that we have to go down deeply and then to the very small scale, and then maybe we can find a key problem or find the solution for these problems. Yeah, that's right. So it's a good way to do the research in the micro nano field. But as an engineer perspective, from the engineer perspective, we cannot go very deep. That's right. So in our center, we cover the scale from like sub-micron to several millimeters, in these scales. So we mainly do two things. One is manufacturing. The second one is to use those things we manufactured, like the objects, like robots or something. So we mainly do these two things, and we have several platforms and the techniques which are like well developed in our center. So today I will give you guys some examples, and then I will move to our organ-on-a-chip. Okay, so like shown here. So mainly the idea for our center is from is the micro nano fabrication or the manipulation, but we want to to develop those techniques towards automation. Okay, so because micro nano things, they are very small, they are not easy to handle, so we need to use some like robotic techniques to help us to do those tasks. Okay, so for the application in our lab, in the center, we mainly most of our applications are towards focusing on the biomedical applications. Okay, so we divided them to like two directions. One is fabrication, so we can do for example like regeneration or artificial tissues, or the microenvironment control for the regeneration tissues. Okay, and if we go small, then like we can control those things we fabricate, or control those tools we fabricate to do what? To do diagnosis. Okay, diagnosis means we need the information, so mainly we do characterization. Okay, so those things we hope we can use the techniques to promote the research for like new materials or new devices that which can be used in biomedical field, or we want to develop some platforms which can promote, or which we can provide some of the intelligent tools to the biomedical field. Okay, so these are the current one of the facilities in Shanghai University of our center. Okay, we have several good like equipment, and we have a small clean room, but everything we want, we can do in our lab, like we fabricate the chip or fabricate or prepare the cell samples or tissue samples. We can do those things in our center. Okay, and then I would like to give you some very brief summary or brief introduction of our previous results. Okay, to give you a more clear understanding about the key platforms in our center. Okay, one is the first one is micro manipulation system. Which it's the key part is the micropipette. Okay, we have developed the automated like cell identification tracking system to use the pipette to for example, to capture the cells or to deform the cells or and we get information. Okay, for example, like here we can get the stiffness, the Young's modulus of the cell. Then if we get large amount of data, then we can correlate with the diagnosis from the doctor. Okay, then we form some model, and this is a good idea back to like almost 8 years ago. And very luckily we published science advances back to the like 8 years ago, and then we have some technical papers in these topics, and I think this system is well developed and it's follow this trying to commercialize this system. Okay, the second one is the materials and the sensors. Okay, so we have several jobs have been done here. For example, like we fabricate, like I said, one thing is fabricate. So we fabricate like micro robots or nanorobots from different materials. So one is peptide-based material, which is very biocompatible because it's a naturally secret material. Okay, and other things like if we use those material, then those materials normally they are soft, so we can use them to do, for example, like physiology, like our like wearable sensor to get information from our body. Then we can do a lot of things. Okay, we have some publication. Okay, and then the third one is the key topic I will talk today is the organ-on-a-chip. So now it's just some video I want to show you guys to understand why it's we call this vascularized, or another word is perfusible. So means the flow, the blood vessels, the whole blood can flow into this device and then to form circulation. Okay, it's similar to the environment in our body. So they have this device or this technique can help us to understand or to do the research. For example, like tissue regeneration, how to regenerate the tissues in an in vitro world, or how we can model the physiology like process, or another very good application for now is to test the drugs inside this device. Okay, and later I will talk introduce the details. Okay, so the fourth one it's the micro or the small robot which we are doing similar to not similar but very close to the idea which are developed in Professor Feng's lab. We use the magnetic capsule, but the purpose for this robot is not to take the image, but to use the the body of the robot as a seal or as a film to cover those leakage or damage of the stomach or the gut. Okay, so this is this work was done mainly was done by the Professor Liu in our center, and she published the NC in this year based on this idea. And the fifth one is the 4D printing, like which means like it's a more advanced than like a traditional conventional fabrication method. It's has the dynamic processing and also can fabricate those we call intelligent materials. Here has some examples. For example, this instrumentation we can like develop or we develop in our lab. We don't use the commercialized fabrication platforms. Okay, and then we have many achievements like those environmental like response structures, as well as the biomedical like artificial like a cardiac patch or those fabricated structure which can be used to implant it in our body, something like that. Okay, this work was mainly done by the Professor Hwang in our center. Okay, and in the center we have many achievements like introduced by Professor Zhang as previously. Okay, then I want to move to the key parts as I call this vascularized organ-on-a-chip. So first, I want to give you guys the background. Okay, so why we need to develop first, like why we need to develop organ-on-chip. Okay, so one of the key needs is from the drug industry. Okay, so like showing here, if we want to develop a new drug, or if we want to look for a new drug, it will take a long time. Okay, normally it's more than like 10 years. Like as you guys know that when during the pandemic we want to develop new what's it called, the immunotherapies or something like that, it takes a long time. Okay, vaccines, it takes a long time. Even though we put like the whole country put so many money for the vaccine screening, but it still takes several years, is right? And it's not 100% safe until now. Okay, so the drug industry is spending so much money, but unfortunately it takes time and it's very high cost, but the risk is very high, because even though we spend like billions of money, and then eventually maybe if we are lucky, we get one drug, but if we are not lucky, so all these things will just invent. Okay, so there's so which means that there are some problems, or some at least some shortcomings we need to overcome, is right? So the first part is from the chemistry. We don't talk about today. And the last part is clinic. Okay, is from the doctor part. So we still remain two testing steps. One is from the in vitro. The other one is in vivo. Okay, so normally we have to test those candidates of the drugs in like the dish of the cells. So normally we call this is two-dimensional environment. Is right. We put the drug in a dish of cells. It's not like in our body. It's artificial two-dimensional cells. So which means that in this environment there is no physiological dynamic environment, which is not I mean, it's not the same as the drug in our body. Okay, so so after this step, they have some candidates maybe succeeded in this screening, but they directly go to the mouse. Okay, so unfortunately, in the mouse, it's a three-dimensional in vivo environment. It's a living thing. Okay, it's a living thing. So it's very difficult to observe those like the drug reaction or those dynamic physiological process in the mice. Okay, so if we want to know the for example the drug how the drug acts on the, for example, the heart or the liver. Okay, we have to sacrifice the mouse, and then those dynamic process was stopped at that moment. Okay, it means that it's good. Okay, it's good, but it's too complex. Okay, so which means that maybe okay, there is a gap. Okay, there's a gap between these two steps, which means that we can jump in, and then if we have one thing, it's like we can put inside, and which is for example is a three-dimensional, which means that the environment is more close to our body, but the controlling of this device or this which we call maybe it's a platform. Okay, it's much easier than controlling the animals. Okay, then I think this is a good one, because by aiding this step, we can decrease those candidates which will move to the animal test. Okay, because animal test is expensive. Okay, for example, now the example here, we will need to test at least 250 candidates. If we can remove those like 200 by this step, then we just need to test 50 by the mouse. Okay, then the cost will be reduced. Okay, this is the idea. Okay, so what about this three-dimensional in vitro environment which we want to put inside? Actually, this is we call organ-on-a-chip. Okay, because it's a three-dimensional, means this is an organ, but it's we want to control, so it should be it need to be in vitro. So this is the idea why we need to develop the organ-on-a-chip. Okay, so the key things is we need to control the environment in vitro, is right. So why we need to control the environment? Because based on the research, previous research, the cells or the biological samples, they always differentiate based on the environment conditions. Okay, here. So means that if we want to develop an organ in vitro, means that we have to control the environment. Okay. So then the next question is how to control the environment in vitro. Okay, now it's there is a technique which you guys are familiar with. Okay, it's microfluidic technique. So microfluidic is a good idea or technique to control, or to at least to construct a three-dimensional environment in vitro. Okay, there's so many examples. I will not spend so much time. I just give you several very like key findings during the development. Okay, one is the long chip. I think this is the beginning of the real concept of organ-on-a-chip. Okay, this is from the Donald Ingham's group from the Harvard University. Okay, then they use the other researchers, they use microfluidic device to develop many other microenvironment like mimicking the human organs. Okay, and then so there are two ways to use the microfluidics to develop organs in vitro. Okay, one we call is direct. I think it's based on the fabrication. Okay, like we call it, maybe it's like a more straightforward way. Okay, like we want to develop an organ, then we can fabricate. We put those cells together to form the shape of the organ. Is right. So there are so many researchers, but the problem for this one is maybe the structure is precise, but it's not, there is no function. Okay, like you like maybe like for example, okay, like you eat the hamburger. Okay, you know the hamburger there is a meat. Okay, the meat inside, but this meat is a what call it's we combine those the meat those not particle but a small amount of the meat, then we put together as the meat, as a layer of the meat. Okay, but it's not the real functional meat as we see in the animals' bodies, right? because we mash them and then we put them together. Okay, it's not the natural way. Okay, so what's the natural way? Natural way is, as I said, it's based on the environment. Is right. So the other way, the second way to use the microfluidics to develop organ is to not directly do that, but use the environment. So this go back to the key advantage of the microfluidics, is right. Use the microfluidics to control the environment, and the environment will stimulate the cells to form the organ by themselves. Is right. Okay. Then this is a good way. Okay. The organs they form are biologically functional. Okay. But unfortunately, those devices normally these devices are like a little bit complex because they want to control the environment, right? So this part we can do. Okay, we will develop some microfluidic device which can be used to control the environment, then to form a type of organ-on-a-chip. Okay, this is the main idea. Okay, so for now the development of the organ-on-a-chip is moving very fast. Okay, there's so many different type of organs are being developed. So recently they are trying to connect them in a small device, as we call like human on a chip. Actually, there is an NIH in the US. There is an NIH program. It's called like the physiological like organ, like a human on a chip. I think I forgot the name, but the main idea is put all those individual organs in a certain system and to connect them, and then to form a man-made, like an artificial human body. in vitro. Okay, this is the developed directions. Okay, so in this direction, okay, in this develop like based on this development, we found that if we want to connect those organs, or if we want to develop one type of organ on a chip, which organ is most important? Okay, maybe this is question. Okay, then we found that no matter what kind, no matter which organ we want to develop, we cannot ignore the vascular, the circulation system, is right. So the circulation system is very important for our body, or also it's very important for connecting those different organs. Okay, even though only the circulation system is a good organ on a chip. Okay, so our idea is we try to solve this key problem. What the problem is? The problem is we need to develop the vascular or which we call the blood vessel organ on a chip. But the key thing is we need to make sure that those blood vessels, they are perfusable, means they are hollow. Okay, the flow, they can go inside. And the second one is they are biologically functional. Okay, why we need to, I try to summarize those several advantages of this device. Okay, I think one thing is we can observe the dynamic process in this chip. Okay, because it's man-made. Okay, it doesn't like the animal. We can observe anything in this chip. Okay, and like this is it's cheaper than the mice, and also we can use human cells. Okay, blah blah, something like that. Okay, so how to do that? Okay, the first one, we try to understand how the vessels form naturally. Okay, they need several conditions. Okay, the first one is the microenvironment. Okay, second one is some of the simulation. Okay, so we have like developed several generations of this device. So today I will simply like briefly introduce the first generation. It's very simple. It's a single layer configuration. Okay, it's very simple device, and it's back to like more than 10 years ago, back to US when I was a postdoc in the UCI, and we generate this flow, and then we found that based on this flow, the cells can form a network exactly the same as the flow pattern. Okay, and mainly this work is done by my senior lab mate, Professor Hwang. Now he's in Shanghai University, and we measured those system, and we found the vessel is good, but the problem is the vessel density is very low because the device is one layer. Okay, so the second generation, I try to and we try to expand this device from two-dimensional, from one layer to three-dimensional, to several layer. Okay, and the several layer gives us many advantages. Like we can modularize this device. We can separate different functional layers. Okay, and it's become very good to use. Okay, and then we test the cells like the anastomosis, means the connection between the vessels. But now it's in the three-dimensional the direction. Okay, and then it's good, and it will form the exactly same vessels like we do in the two-dimensional. Okay, and then we do many tests like the perfusion and also the quantification. We found that the vessel density now is increased a lot. Okay, now it's compatible to our body. Our body is around like 30 to 40 this number. Okay, now we can more than 10. Okay, and then the perfusion looks good, and the blood is flow freely in this system, and we can use this one for this purpose. Okay, then we have some thing we want to do. Then we go to the third generation. Okay, for now we use the modular perspective from this device, and then we also develop a type of porous membrane to separate them, because the second generation only we can do is like limited to 2 layers or 3 layers. By adding this porous medium, we can if we have money, we can expand this device to several hundred layers. That's possible, but it's very expensive. Okay, then we call this as magnetic configuration. Means we can we can freely change the shape of the tissue chamber, like I showing here. We can do like triangle or rectangle or other way. Then this device gives us one of the advantages, which means that we can generate various like different type of flow in this channel or in this device. Then we can connect the condition of this flow with the final formation of the vessels. Then we can have some, we can like this advantage can help us to solve some problem, which is how, for example, like which condition can cause what type of shape of like the flow, the vessels. Okay, we do a lot of like quantifications. Then we found one, this is not published, this is ongoing research. Then we found that the flow, one of the flow parameter, which is shell stress, it's a key parameter to stimulate the blood vessel growth. Okay, but there is a limitation. Okay, the lower one is good, but when it reach a limitation, it become inhibitor for the blood vessel growth. Okay, and the second one is we can use this one to have to make sure that those biology scientists, like we can use this one as a tool, as a good tool for biology scientists to pursue other like key problems they are interested. Okay, and as the conclusion, we for now for this type of organ, like the vascular or the blood vessel organ-on-a-chip in our lab, we are trying to make this device to be more easily like a use, or it's more friendly for the other, for example, for the researchers from other fields to use. Because for now this device is a little bit complex. Okay, and it needs a lot of equipment to make it functional. Okay, for now we are trying to use this to make it more compact and more easy to use. Another one is it's a scientific platform. Okay, so it's a, we can put different input into this system and we measure the output. Then we can get the connections between them, and then this information will help us to answer many unknown questions. Okay, another one is we will use this device to overcome those shortcomings from the drug industry. Okay, and for the center, for now we have these several platforms. We want to use this platform to develop like new materials or structures or devices to help improving the techniques for the biomedical industry or biomedical society. For the last, I would like to thank the funding sources from our government, and also I want to thank the colleagues in our center, and especially the Professor Xie, who is the dean of the School of the Computer Science, and also the Professor Liu and the Professor Wang. And also I want to thank the collaborators from many friends and like mentors who help who have helped me a lot during my career. Okay, and these are at last I want to thank all my hardworking students, and without you guys we cannot have these wonderful slides. Okay, that's all. Thank you.
Great. So, Tao, yeah, you came to Shanghai not a very long time, but really did a very interesting work. So, congratulations. Yeah, now let's move to the panel discussion. Let me first introduce our panelists. Yeah, today we have two beautiful young ladies as a young scientist as our panelists. First is Jiaying Zhang. Jiaying got his PhD was from Tsinghua University, and then moved to Beihang for a postdoc, and now as a researcher at the Peking University Third Hospital. So as doing a lot of work, I think related with all this topic. Welcome, Jiaying. And our next panelist is Bai Xue. Bai Xue got PhD from the Chinese Academy of Science. Also looks like you are physics. Yeah, you do a lot of work, from physics. Now Bai Xue was associate professor and Capital Medical University. So yeah, welcome Bai Xue. So let's everyone get on the stage. I think is all of you here. Yeah, please turn on your cameras. And we start the questions. So yeah, our two ladies panelists, who goes first? Bai Xue, maybe. Yeah, yeah. A, B, C, Bai. B.
Okay.
Please.
Thank you, Professor Zhang, for your introduction. I want to ask to Professor Feng. Yeah,
Okay.
Professor Feng, you have done very much wonderful work, and I want to see beside the tumor target therapy, and do you think what other application for the micro-nanorobotic in biomedical?
You mean
beside
for
the
other,
beside
for
the
any-
tumor cancer, beside the cancer therapy, and what other application for biomedical?
You mean the only for the biomedical? Because I see many researchers in the micronanorobot area, like just a moment ago, Professor Hwang showed us some micronanorobot can do the cleaning the environment. Yeah, even though it's outside of the body, but I feel it's quite interesting. And as I know, many researchers in the biomedical area, so micronanorobot can do the assay, like the analysis of some chemical materials, like in vivo. Yeah, not in vivo, in vitro, like on chip. I think in today's talk, the Professor Tao Yue also introduced some organ chips. So by combination, I think he shows some very good examples, like the combination between the micronanorobot technologies with organ-on-chip technologies. So he gave us many interesting ideas, not only just using the micronanorobot for the drug deliveries. And he showed some organ-on-chip utilizing the micronano technologies. Because the robotics technology, I think, is quite huge. It's a wide definition. So any kind of, as I showed in my slides, any kind of the technology using the micronano based on the micronano size, plus with robotics technology, as Professor Hwang this talk. He introduced many control theories like PID control theory or fuzzy control theories. Yeah, because of time limitation, I only show some applications. I showed many videos. I think it's easier for the audience to understand what a micro-robot can do. So if you are interested in the fundamentals, we maybe in the future we can discuss in the details. I think that's all my answers. I hope my answer answered your questions. Okay.
Okay. Thank you, Professor Feng. Yeah.
Okay. Thank you.
As you said, Professor Hwang had made many kinds of micro-nanorobotic. One of them can remove the garbage from the liquid. So as you know, some blood decision caused by some garbage in the blood. So I want to ask Professor Hwang, does this kind of micro-nanorobot can be used for human blood purification? means I means the micro nanorobot remove the garbage from the blood.
Yes. So you mean in vivo? You're talking about in vivo? Okay, in vivo. So we are not yet there, but we are in short term as we are targeting to treat this blood clotting, blood coagulate clot. So that usually because in the cardiac disease and this pulmon lung, and we develop this artificial lung, which is not a bit different than organ-on-chip, because organ-on-chip is more simplified, more like a small scale organ. But what I'm interested is to a bit like to make a replicate, not replicate, but like really like a lung scale artificial lungs. So which makes like high volumic blood flow rate, like 4 liter per minute. So that in any kind of today, this ECMO, extracorporeal oxygenators today in medical environment have a very short lifetime due to this blood clotting. And now we are studying this artificial lung platform with this human endothelial cells to avoid these immune reactions, and also this to design wise to make this shear rate and shear flow rate, everything to carefully deal with the hemodynamics to avoid this blood clotting. And then, but still we cannot avoid this clotting and there's some garbage. Then microbot, we can send the microbot inside to make some troubleshooting. It's a robot. So that's what I think is would be some in near future.
Okay. Thank you, Professor Hwang. So I want to ask Professor Yue.
Please.
Yeah, the organ on the chip is very important. Yeah, especially for the biomedical research. But I want to get the organ on the chip, especially for the functional organ on the chip. So I want to know, in your opinion, Professor Yue, what have limited the application of organ on the chip? Yeah.
Okay. Thank you, Professor Bai. Yeah, it's a good question. Okay, like, okay, okay, I will repeat your question. Okay, so you mean that you need or you prefer to those functional organs? Okay, like which means that you need the size to not too small, but you want to like relatively large size of functional organs, which are man-made. It's right.
Yeah.
Okay. It's a good question. Okay, so I think the limitation. Okay, limitation is I think first one is the cost. Okay, the first one is cost. Okay, because if we want to really like you want to realize these functional organs, like artificial organs, you need to use specialized, for example, the cell source as well as those growth factors. They normally they are very expensive. Okay, like if you imagine like the size of one, for example, 1 microliter, the size. It's the volume is 1 cubic millimeter, is right. I think you know that in this small volume there are, I think, more than 10 million or like several, like maybe 100 million of cells. Okay, if you count this number, only these cells will cost very like a lot of money. Okay, so I think the cost is the first one. Okay, the second one is, I think it's back to the key topic I talked today. So I think the second one, if the artificial organ if the size of the artificial organ go to a little bit large, then it's very difficult to diffuse or to like transport the nutritions into the cells which are located inside the organ. Okay, so means that this organ needs to have a very good like blood vessels inside. Okay. So for now, what I talk about today, we can succeed in like several hundred micrometer thickness. Okay, like if go to thicker than 1 millimeter, it's a little bit difficult. Okay, this is one thing, because the flow, as I mentioned, I use flow to generate those vessels, but the flow cannot do like penetrate very thick, for example, the hydrogels or the ECMs. Okay, so maybe we need to use external force, for example, use pump or other things to generate flow pressure to make sure that the thickness can be increased. But for now, I think there is a limitation for this size in terms of the vessel system. Okay, I think this is second reason which limited the organ size. Okay. Yeah,
Okay,
that's all. Okay.
Thanks, Professor. Yeah.
Okay, how about Jia Ying? Yeah, Jia Ying, please.
Firstly, thanks for your Professor Zhang's introduction, and I'm honored to participate in the conference and would like to express my sincere appreciation to the three speakers for their excellent presentations. As a biomedical researcher, I'm more focused on the biomedical applications of the micronanorobot. So I have small questions to ask Professor Feng. The first question is, the micronanorobot can move against the blood in vessels. So I want to know whether the micronanorobot can move according to the rotation in the vessel, and how to observe this process.
Okay, that's very good question. As I mentioned, why we put some photosensitive particles on, like a photosensitizer, on the surface of the micronanorobot, because our human body is not transparent, so it's hard for you to observe all the processions. So that's why actually currently we try to using the infrared image, like using there is many different kind of ways. One is using the photosensitizer particles. Another thing is you can using the photoacoustic imaginations. And for other image technologies, like you can use in the CT scan, X-ray scan, or MRI. So there is many imagination technologies can observe the human bodies, like when we goes into the hospital for the healthy check. So there is many technologies, but for the micronanorobot, there is a big issue. We have to see the micronanorobot in real time. So if you're using the MRI system or the CT scan, it will cost several seconds. Several minutes. So it's not in the real time. Then you will lost the position of the micronanorobot when when it's moving in your blood vessel systems. So for the currently, not only in my lab, I think many researchers who is focusing on the drug delivery research topics, they try to using many different kind of ways to find out which is the best way to observe the micronanorobot in the blood vessels. I think the potential way, for my opinion, one is using X-ray. It's cheap and easy, and it's in the real time. The second one is maybe using the photoacoustic imaging. So, but the problem is the depth. So if you want to observe some very, very in very deep very deep in your body, so maybe hard to see. But for the surface of our human surface skin, so it might be possible. I think for the MRI or the CT scan, it's cost quite a long time, maybe not that available. I think your question also related to some like a rotating control of the electromagnetic coil to like the microrobot, it's rotating in the blood vessel. So currently, we can achieve some upstream control of the micronanorobot in the blood circulating system. However, our blood flowing, the speed of our blood flowing is quite different. The gap, there is a big gap between the maximum to the minimum. So the maximum can go to the 2 meters per second. The minimum can go to the several micrometer per second. So the environment, that's why the micronanorobot for drug delivery in our human body is challenging. The environment in the human body is quite different in different parts. So that's why current our strategy is we just concentrate the electromagnetic field, for example, on your brain or on your heart or on some area of your skin. And when the micronanorobot swarm, so they passing through this area, they will get trapped by using the electromagnetic field. So that's our strategy. Our final goal, like ultimate goal, is like in the science fiction. So we can control the real microrobot, go anywhere you want. But I think it may take all the researchers' effort, like in today's talk, Professor Hwang, me, and Yue Tao. So we need to spend a lot of time. Maybe I hope it can be achieved in 10 or 20 years. So before I die, I want to see this happen before I pass away from this world.
Maybe I have a following question, for this. I think you follow Brad Nelson's work, right? So Brad Nelson has used the strategy, same thing, have a huge, magnets outside and, very complex, the magnetic field, multiplication. So I'm thinking that, use these magnets, to control or manipulating inside, the microrobots. Is that, did you consider about this, the magnetic field will affect our body? Maybe.
Okay. That's a good question. Actually, Professor Brad Nelson is a pioneer of this research topic. So he started for this research topic, I think, more than 20 or 30 years. So I only started, I only jump into this research area for around 10 years or 15 years. So, but I think this research topic is quite interesting and challenging. And I think it's worth to spend my whole life to focus on this research topic. Back to your Professor Zhang's question. So actually, from many research articles, if the actually current electromagnetic field, the strength is lesser than the MRI system. So our system is not that high. It's not caused that damage to the human body. And we are trying to increase it to 10 Tesla. From some publications, the strength under the 10 Tesla is safer. It's safe for the human body. But if we goes up to the 10 Tesla, currently we don't know because we don't have the data. If we want to increase the electromagnetic field that's strong, so our system will be very, very huge. It's maybe even bigger than the MRI system. So it will as Professor Yue told many times, is the cost. So we also have the problem of the cost. If we want to make our own MRI system, the cost is too much. Maybe more than 3 million RMB or something more. Yeah, that's my answer.
Okay. Yeah. Super. Thank you. Yeah. Jiaying, please.
Another question for Professor Feng. You know, the optoelectronic-tweezers can manipulate and distinguish the specific cell types. So I want to know whether the optoelectronic-tweezers can distinguish the healthy or unhealthy sperm. I think maybe is essential for the sterile human in clinical trials.
Yeah, that's also a good question. So currently, to distinguish the sperm, the healthy or unhealthy sperm, only by using the optoelectronic field is difficult, because actually the fundamental of such kind of control is because the conductivity differences between the good cell to the bad cell. So for the sperm cell, we can separate from the live cell to the dead cell, because the conductivity is quite different. But if you mention about the healthy or unhealthy, that's quite difficult. But we can using the microscopy system, using the image, to see if this sperm don't have the tail, or this sperm have two head, and we can see the difference between the sperms. And then we using the optoelectronic tweezers, we can separate it. And this is my answer, I think.
Yeah, thanks for your answer. Okay, Professor Hwang, I have one question. So you cite the micronanorobot swimmers have the functions such as the cargo transport. So I want to know if the swimmers can load some drugs like moleculars and siRNA to deliver these drugs to the human body. Do you have some in vivo experiments or some results for this?
So unfortunately, I haven't done that in vivo experiment, because nobody want to do this test for now, because
such as in mice.
It's so dangerous. In mice, in even a mouse. Yes, I think it's quite also, because when my environment, I'm in France, and also it's quite, they are quite reserved for this kind of test. That's why, you know, they more interested in this artificial environment, to my artificial organ, to make all these kind of test essay. And then once we prove this, then we can go to next step. I think that's why I think we didn't do real in vivo test, animal test. But you know, if I choose to physically, I can answer this question, because you know, in vivo environment, there's blood flow, and the major concern is, as soon as we put in a it's a blood circulations, the micro swimmers swimming, can easily carry away. Then we need very high dynamics to be swim against. That's my physical concern. So now I think we are very trying to answer this fundamental question, to be able to how to efficiently overcome this flow, and how we can make this get immobilized. We have some acceleration, brake, and the underflow. So that is, I think we don't really, for now, to this study, we are animal. We don't necessarily to this. We have sufficient challenge in a physical challenge, so we can test in artificial environment. And but I think this can be somehow, in a short term, few years, can be solved, I feel, because there will be a magnetic field limitation and the optimization, and also maybe we are getting more and more integrated system, so the swimmer itself can be more integrated, so it can have more self energy source, and then which was not really possible before.
Yeah, a small question for Professor Yue. It's amazing and interesting for your work, the micro-organ formation on a chip. So I have a small question. I'm so curious, what's the key parameters in the microenvironment that influence the micro-organ formation, such as the temperature or pH value or of some cytokines?
Okay. Thank you for Thank you, Professor Zhang. Thank you for your question. Okay, it's a good, very expert question. Okay. So as I mentioned, the environment is the key to stimulate the formation of the vessel. Okay. So for example, the temperature, we have to make sure the temperature is like 37 degrees. So we put the whole device into the incubator. Okay, like the same. As you incubate the cells, for example, the human cells need in the incubator is 37 degree, and the 5% of carbon dioxide, something like that. Okay, so the environment is the same as you culture the cell, but I think the key parameter is the physical properties. Okay, physical means what? Means the flow rate, the flow pressure. So we have to compare to the similar flow, like blood flow in our body, like the flow inside our capillaries. So now I can tell you is we found that it's around how much, like around 50 Pascal was for just a moment. We use water to generate those pressure. Okay, we need we use the gravity force of the liquid. Okay, so if you put the liquid, the height of the liquid, the water, okay, like the culture media, similar to the water. Okay, if you put the maintain the height of the liquid around 1 centimeter, like 10 millimeter height, I think a 10 millimeter height, the pressure is around, I think it's around 10 or 100 Pascal. I forgot. Like those pressure is enough to generate the flow as well as the shell stress force to stimulate the endothelial cells to form the vessel shape. Okay. I think the flow is the key. If you are interested, you may check my paper or something, but I may confuse the data, but the height of the liquid is around 1 centimeter. Okay. And another parameter is the time. Okay. The time means you have to make sure that the device is like the device is formed in a relatively short time. Means the cells, if you harvest the cell, you have to make sure that they go into the device quickly, like less than 1.5 and 2 hours. Okay, then then you observe the cells. If the cell is not good, which means that if the cell are not they don't form the vessels in like 3 or 4 days, means this cell condition is not good. Okay, so the time, they have a time stream, like normally if the good cells or the right procedure will let the device to generate the vessels less in like less than 8 days or something like that. Okay. I hope I answered your question clearly. Okay. Yeah. Okay. Thank you. Okay.
Yeah, so nice. Yeah, so maybe I follow that. So for organ on chip, I know, yeah, it's a really hot topic. A lot of people was working on, and also a lot of patients was waiting for your results. Yeah, because it was for the personalized the the treatment, all this, medicines is really, really work. I like your ideas. You make that all this like different chambers, different layers as a standard, right? Like standard modules, right? We can change out easily, to fabricate that like that. So for all these, organs, I think they have many different kind of different functions, right? Or different. So for your standard, is that can be used for unified to be used or just specialized in some field?
Yes, thank you, Professor. Yeah, I think you it's very, very good question. Okay, so like you mentioned, actually, as we know that our human body, we different organs, they are formed by different cells, right? So if we want to make several type, like different type of organ or chip, actually we have to use different type of cells. So, and as I mentioned, different cells, they need different environment, is right? So eventually we have to develop like a specialized structure to generate special environment for special cells. I think this is the thing. But currently there are some researchers, they are trying to follow another like a direction, which they use stem cells. Okay, they use stem cells, which means that they can use one type of cell, but these cells will differentiate based on the environment which created by this device. Which means if you design a device, but which means that the cell source, maybe we can use one type of cell, maybe the very like basic the stem cells, like IPS or something like that. Okay, but the environment, I think we cannot make a unified environment, because this is the human body is a little bit like complex. I mean
too complex.
That's right. That's right. So yes, that's my answer. Thank you.
Okay, great. So for Professor Hwang, maybe my last question is for you. I like you the last part of you didn't have time to go through that, the 4D, the 4 dimension. The structures of the device. You have in the last part for the 4D,
Okay.
So I saw that is a very smart idea. I want to know more about the materials. Did you use what kind of materials to make this?
What kind of materials? So 4D, we use more for the future potential biomedical applications, so biocompatible polymers, which is commonly used PDMS, with people use it for silicone elastomer, or we can have this with the 4D structures with the elastomer, with the mixture between the PDMS and here for the magnetized, we do this magnetic particles mixture, but we have this local magnetization, programming. So it's not same magnetization. So we have our own homemade custom system to fabricate, because it's not standard to fabricate
Okay, I see. That's a very interesting work. I love that ideas. I think a lot of people was online, following this. Someone say, "Okay, guys, you guys are talking about something really out of the field, like UFO, outer space." So today we are really draw a lot of attention. I can ask. On the website, we have more than 15,000 people there. So we have another kind of 10,000 people on the WeChat. So we got a science, net was broadcast today. We have more than many people was following. So the very hard topics. So great, congratulations to all of you. And also today is a big day. We opened the channel on the LinkedIn. So today was the first time I was on online, show on the LinkedIn too. So congratulations for all of you. So it's my time to do my last job, I think today, Feng Lin really answered the questions, right? Yeah. So yeah, you did a good, wonderful talk, and now you have your certification. I will send you later. Okay. Yeah, Professor Hwang. Yeah, thank you for your wonderful talk and wonderful, answers. Yeah. So you have a certification. I will, share with you later. And Tao Yue, yeah, this is for you. Okay, keep on going for this organ-on-chip. I think it's really, really kind of useful, technologies. Yeah.
Okay.
So great. Yeah, next week we're going to have also. Okay, forgot this. Okay, yeah, ICANX this year and July and summer we will have a big go together. Go to Davos. So Brad Newson will be there. Yeah, he will share, the latest, the robots, the micronanorobot. I think we can, have our next, discussions or panels and Davos. So welcome all of you to join us. Also, Feng Lin, you have industry, right? You already have your company. So you're right match to be entrepreneurs. Yeah. So welcome to, join us this big go together. So will be a big party. And next week, we're going to have another group. We have Professor Philip Zhou from Hong Kong U. We have another Korean scientist from SNU, Seoul National University. We have another one was from UK. So we'll be a big go together to talk about molecular electronics. So ICANX every week was here for you. Tuesday, youth talk. Friday, ICANX, the seniors talk. Okay, please follow us. Thank you very much. Okay, yeah, thank you.
Yes.
Okay,
Thank you very much.
先生、女士们、亲爱的朋友们，欢迎大家来参加我们的 ICANX 达沃斯科学峰会。那今年是第一次 ICANX 会组织大家一起在瑞士的达沃斯进行线下的聚会。我们有6个主要的议题。第一个是创新 innovation， 第二个是科学 science， 第三个是 technology 我们的技术，第4个是 investment 投资，第5个是 management 管理，第6个是 entrepreneurship 创业。所以它结合起来就是 It's time 是时候了，是时候让我们去达沃斯听这些非常给我们启发的关于未来的这些报告。在达沃斯我们会有3个非常重要的论坛，一个是诺贝尔奖论坛，我们会邀请诺贝尔奖获得者来跟我们谈科学的未来，我们会邀请世界科学院的院长来跟我们谈世界科学技术发展的未来，那我们会邀请大学校长来参加我们世界大学校长论坛，来跟我们谈关于教育的创新教育的这样的一个未来。同时呢，在达沃斯呢，我们也会邀请各行各业的这样的一个非常重要的领袖人物、领军人物来跟我们分享他们的所思所想，他们对未来的思考。那我们也会邀请非常多的各行各业的精英来跟我们分享他最精华的这样的一个思想。那当然了，达沃斯这个舞台也不只是给这些大牛们展示的舞台，也是我们来展示的这样一个舞台。所以如果你有好的故事、好的思想、好的技术、好的思考来进行分享，那也欢迎你再来线上投稿。所以我们的截止时间是4月1号，大家还有1个月的时间来准备好你的发言，希望分享给全世界的。所以欢迎你在线提供你的资料。那我们也希望你成为这个舞台上的明星。那在达沃斯呢，我们设了3个奖。第一个是针对大学生的，你是创新创业的最牛的大学生，那你来申请我们的创新奖。 如果你是一个毕业10年以内，现在正在从事独立科研工作的科学家，那你来申请我们的青年科学家奖。如果你是一个创业者，你成立了你的公司还不到5年的时间，已经发展得非常好，那请你来申请我们的创业奖。所以所有的奖项申请的时间截止都是4月1号。那欢迎大家在线提供这样的一些资料，那我们也会给大家非常多的这样的机会，成为舞台上最亮的星。那是时候来我们大家一起把科学推向未来，推向世界。那这个呢是我们在达沃斯的非常非常重要的合作伙伴，我也希望你成为我们的合作伙伴，我们一起来推动世界的发展。那现在达沃斯论坛已经开始注册了，所以各位朋友、各位好朋友们，请你们开始尽快注册吧。我们相聚在达沃斯，我们一起 Go Summit 走向巅峰。
在持续发展的社会中，电子元器件需要应对日益复杂化的要求和越来越高的期待。技术革新浪潮汹涌而至，对其高性能的需求、无限小型化的追求，成为行业发展的必然趋势。多层陶瓷电容器、电感器、高可靠性元器件